Ladies and gentlemen, welcome to the Big Bear Math channel. And today we're tackling AP Calculus BC. We're looking at the exam from 2018. We got question number 5. And I tell you what, is there anything else you'd rather be doing right now than tackling a polar question? Yeah, we're going to tackle a big polar bear today. So here is the gist of it. We've got two functions already drawn for us, which is outstanding. So r equals 4 is going to be this nice circle here. So, and r equals 3 plus 2 cosine of theta is going to be this little limicon with a little dimple, rolling dimple right there. So it is smooth. It's differentiable regardless of what I draw. Okay, so there's my two functions. And they even told us where they intersect. Does it get any better than that? All right. So they're going to intersect once right here at pi over 3. So I'm going to draw a radial line there. Okay. Imagine a straight line. And then they intersect once again at 5 pi over 3. Okay. In part A, as you can imagine, wants to find the area of the shaded region R that looks like a nice crescent-shaped moon almost. So we're going to dive in and try to find the area bounded between these two functions. But real quick overview on how we're going to attack area. So I'm going to set up two integrals initially. But you can certainly, and I'll try to remember to show you at the end that it could easily be condensed down into one integral. But I want to first, the reason I'm going to think of it as two integrals is I'm going to do an integral from pi over 3 to 5 pi over 3. And what I like to do is I think of these radial lines as sweeping, almost like the wiper blade on your car. They're kind of rotating in a counterclockwise motion, okay, all the way around here. Okay, so I'm going to do one integral to find all of, basically everything inside of r equals 4 from pi over 3 to 5 pi over 3. And then I'm going to come in with a second integral and try to find all the area bounded within this limicon. All right, and again, I'm going to draw these wiper blades. I'm rotating counterclockwise. I'm pivoting around the origin or the pole. And if nothing else, it's got a little color to it. Basically what I'm going to do is I'm going to subtract all of the orange area away from the green area. So by the time I subtract the two, I'm just left with that shaded region. So area in general of bounded by a polar curve is going to have a built-in coefficient of 1/2. That's automatic. And it's going to be the definite integral from, say, alpha to beta, or you could use theta sub 1 to theta sub 2 of the function r squared d theta. So that's the most generic form. In this particular case, let's see if I can get my pen colors to kind of match up with what I shaded there on the front. So the first integral is going to be from 1/2, we'll go from pi over 3 to 5 pi over 3. And that was everything inside of 4, r equals 4. So all those wiper blades or radial lines, the tips were always bounded by that function. Then we're going to add, switch to, I think we had an orangish. Okay, now we want everything bounded within that limicon. So we'll go 1/2 pi over 3 to 5 pi over 3. That time r was equal to 3 plus, let's say, 2 cosine of theta. That's got to get squared, d theta. And especially when I'm first teaching my area bounded by a polar function to my new students, I really stress the two integral setup here. Now, ironically, oh gosh, why do I have a plus sign? I bet you guys were screaming at me back home. Let's get rid of that bear. Maybe I can erase it all together. Woo, baby. Glad we didn't lose that. Okay, so this is just going to be a minus. So we've got everything inside of r equals 4 minus everything that was inside r equals 3 plus 2 cosine of theta. Now, because these two integrals do share the same bounds, we can kind of condense it into one integral, but I wouldn't say it's a huge advantage. So we've got these bounds, and you've got the 4 squared minus the 3 plus 2 cosine of theta squared. One of the reasons I try to emphasize kind of the two integral setup early on in our school year anyway, at least, is I want them to know that like this function here is getting squared by itself separately from this function getting squared. What I've had in the past is sometimes students will start to think that this right here, let's see if I lost my, okay. But anyway, they'll do 4 minus the limicon first and then square the entire quantity. We want to make sure we don't do that. Now, what I do think is very helpful, though, is to take advantage of the symmetry in this function. And I could say, you know what? Instead of integrating from pi over 3 all the way to 5 pi over 3, what I could do is go from pi over 3, stop at pi, and then double that answer, which gets rid of this guy. Same thing here. Stop at pi, and then double that answer, which gets rid of that guy. And the nice thing there, because everything that's above the x-axis is equivalent to everything below the x-axis. So that, especially if you ever had to evaluate one of these by hand, that would be a huge advantage that I highly recommend. Part B says, hey, let's find the slope. All right, slope of the line tangent to this graph at pi over 2. So what we're going to do is let's go up there. Let's shimmy up there just a little bit. And let's see if we can at least attempt to draw a tangent line right there. It's going to look like this. Man, wow, that's one of my better lines. I got to admit, mine are usually way worse than that. So we're going to try to find the slope of that line. And if nothing else, we kind of know that it should be positive. If I do all this fancy work and we get a negative answer, big red flag, we're going to come back and try to figure out where we went wrong. So let's try to explain slope within a polar function. Okay, so the slope of a polar function is probably the most complex version of slope that you're going to run into. So at the end of the day, slope is always going to be dy dx. It's always going to be rise over run. It's always going to be your change in your y divided by your change in your x, no matter whether you're in rectangular function, working with a polar function, working with a parametric function. It's always going to come back to that definition. It just happens to be in this case, the derivative of y has to be done with respect to theta, and the derivative of x has to be done with respect to theta. And what you have to know off to the side is that y is in polar mode defined as r multiplied by sine of theta. And so what you're going to have, and it's r times, and r itself is a function of theta. So we have to use the product rule right there. And it's going to be the first times the derivative of sine of theta plus the second function times the derivative of r with respect to theta. Okay. And then you also have to know going into this that x is always going to be equal to r cosine of theta. So deriving that with the product rule is going to make r times negative sine of theta. I'll put that in parentheses because of the negative. Plus cosine times the derivative of r. So that's my version of the product rule. Okay. And then what we're going to do now is we need to evaluate this derivative at theta equals pi over 2. So one of the things we got to do here is figure out, what is the value of r when theta equals pi over 2, or what's the value of dr d theta when theta equals pi over 2. So if you recall, let's see, r was equal to 3 plus 2 cosine of theta. Let me double check that in my notes, make sure I didn't screw that formula up. Yeah, I think that's right. So if I evaluate r of pi over 2, I'm just going to get 3. Now, in this case, the derivative of r with respect to theta is going to be negative 2 sine of theta. And evaluating that function at theta equals pi over 2 is going to make negative 2. So I'm going to substitute the 3 for all the r's, the negative 2 for my dr d thetas. And let's see what this is going to look like here. So r was a 3. Cosine of pi over 2 is going to be 0. Sine of pi over 2 is going to be 1. Thank goodness they gave me pi over 2. They could have given me worse. Like if it was pi over 3, pi over 6, something like that, pi over 4, we'd have had our hands full with some nastier numbers. So I'll take pi over 2 any day of the week. Let's see. We got ourselves a 3. We got ourselves a negative 1. Cosine is going to be 0. Dr d theta is going to be negative 2. So we wipe that bear out. Negative 2 divided by negative 3 is going to make a positive 2/3. Thank goodness our answer was positive. As our drawing earlier indicated, we were hoping and expecting a positive answer. So here we go. We've got a particle moving along that limicon, 3 plus 2 cosine of theta. And let's see. The particle moves in a way such that the distance between the particle and the origin increases at a constant rate of 3 units per second. Now, I want to pause right there. This distance they're talking about between the particle and the origin, that they're referring to r right there. So r by its very nature is the length of that radial line that connects the origin to the curve itself. So basically what they're saying there in that sentence is that dr dt equals 3. Now, why did I say dr dt this time? Notice how it's 3 units per second. So I know that the derivative is with respect to time. Now, what they want me to do here is find the rate, find the derivative of theta with respect to time when theta equals pi over 3. So this is actually going to be a lot easier than it may sound right here. All right, I know what you're thinking. You're thinking there's no way that this problem is going to be easier than but it really is. So we already know that r equals 3 plus 2 cosine of theta, right? Let's derive this equation with respect to t. So we get dr dt equals -2 sine of theta. Now don't stop. Remember, you got to derive that inner function now. So it's d theta dt. Real quick, let me get my 2 cents in here. Like when you're deriving this function, cosine is your outer function. And so we're basically applying the chain rule. So you get sine of theta and then multiply that by the derivative of that inner function to get d theta dt. Now, we want to evaluate this equation when theta equals pi over 2. No, I said that wrong. We're going to evaluate it at pi over 3. So here's the deal. We already said dr dt is always going to be 3, they said. And then we got -2 sine of pi over 3. And d theta dt is what we're trying to solve for. We're trying to find the rate at which that angle is changing. Let's see. The sine of pi over 3 is going to be radical 3 over 2. So then the 2's cancel and you just get negative radical 3. So we could say d theta dt equals, let's see, -3 over radical 3. That would be radians per second. And then, of course, you could rationalize it to just get negative radical 3, but that wouldn't be mandatory. So I hope that helps. That was one of the nicer polar questions. I actually really enjoyed that one. If you found this video helpful, please hit subscribe below, share it with your friends, and let's go get a 5 on this exam together.